So here we go. I think we're recording now. So last time we ended class, we were talking about cross-validation, and it was all on paper though. So I thought I would do a little bit of Python code with cross-validation too. So there's several different kinds. The Wikipedia article on this topic is very good, so you can read that if you want to. What this little GIF here is showing is threefold cross-validation. So you take your data set and then you scramble it, and then you partition it into three different parts. And so so the blue here is the test set. So you train on the red and then test on the blue 3 different times. So every point in the data set gets a chance to be a training point. Actually, it gets several chances to be a training point. And then every element of the training set also gets a chance to be a test point. So then you average the performance of these 3 different models, and that's the threefold cross-validation score of whatever hyperparameters that you're considering. So remember that the point of cross-validation is to tune your hyperparameters without ruining your test set, in the sense that the performance on the test set is supposed to be an estimate of the out-of-sample performance of the model. But if you use the test set for like deciding between a bunch of different hyperparameters, then it's going to work less well. You're going to get an optimistic prediction of out-of-sample performance. So it's better to use cross-validation to choose your hyperparameters and then reserve the test set just for estimating out-of-sample error. So yeah, so I was just shopping around for data sets to use to demonstrate this stuff, and I found one called Forest Fires, which is one of the most popular data sets on UCI machine learning repository. And it's advertised as a very hard regression problem, but it's a ridiculously hard regression problem. I actually couldn't get a positive R2 score. And then I spent all this time like wrangling the data too, so I didn't want to take it out because that would be, to admit, wasting all that time, which I actually did waste. But what these are facts about regions in Portugal, I think, and the target variable here is this last column, which is the area. That's the area that's burned in the forest fire. And it has a real tendency, it has like 0 is very overrepresented here. So I change all the months to numbers and change all the days of the week to numbers. And then we just do a test train split and scalar and stuff. So I thought about replacing the y values with their logarithm, because you can see the y values here. This is a regression problem. This is area burned in the forest fire, and it really clusters towards 0. So I thought maybe if I applied log to that, it would spread out the values, and that would make regression work better, because I was having a hard time getting a positive R2 score. But that didn't help. In fact, it made things worse. So, but anyway, that's kind of interesting of itself. So the library that you use to do cross-validation and sklearn, there are a couple you can use, but one of them is cross-val score. So here I'm getting a support vector in regression mode. sklearn calls these things regressors, which I guess is a word, but I've never heard it outside of the sklearn documentation, but I like it anyway, and I always want to use it. So here's the support vector regressor. And here it has two parameters here. C is, do you guys remember from our discussion about support vector machines, what is C? You know, because you don't have the perfect margin, there are slack variables. And so you, as part of what you're trying to minimize, you minimize the amount of slack that you use, but you weight the slack by C. So by making C bigger, it makes slack more expensive. And so slack is for margin violations. So C is how much slack costs, basically. And then remember that by default, support vector machine uses the RBF kernel. And the RBF kernel has this gamma, which we talked about last time. And that's like, you know, the RBF kernel function measures the similarity of 2 points. You could think of one of the points being kind of like a landmark mountain. And then the RBF of 2 points is sort of how far up the other point is on this mountain. And by making gamma bigger, you make the mountain taller and skinnier. So anyway, here's two hyperparameters for support vector regression. And so now you can get the cross-val score. You just pass it the model, the training set, the testing set, and this is how many folds you want. So here I did 5 folds. It's really common to use 10 folds, but in most of the examples in this worksheet, I use 5 folds. So here I just I chose a bunch of gammas. This is more than I would normally explore, but the scores were really bad, so I got kind of desperate. I even started changing epsilon. You guys remember what epsilon is in the context of support vector regression? Epsilon is like how wide the margin is, and when you're doing regression, you want to pack all the points inside the margin. So epsilon is like the width of the street. So we have these 3 hyperparameters. We're trying all kinds of possibilities here. And every time we go through, we're doing cross-validation with 5 folds on the training set and the model here. So then the output is each model has 5 scores, 1 for each fold of the cross-validation. And then you average those to get the performance of those hyperparameters. So this is the performance on each of the 5 folds, and then here's the average across those 5. And these are R2 scores, and you can see that they're just awful. So all of them are negative, and the best one that was found is like 0, but it's still negative. So this is just ridiculous. And then I tried the I tried the random forest regressor, and it basically does even worse. But that still illustrates what you want to do in terms of using cross-validation to explore hyperparameters. So because that was such a disappointment, I decided to do it again with the, so this will be a classification problem with the iris data set, which we talked about last time. So this is like iris setosa, iris versicolor, iris virginica. So there's 3 different kinds of iris, 0, 1, and 2. So this is a multi-label problem. And there are four features, sepal length, sepal width, petal length, and petal width. Okay, so I'm going to use the support vector classifier. And so here's a bunch of values to try for C, and here's a bunch of values to try for gamma. And then I thought this time it might be fun to turn it into an image. So I'm making an image here called M. And I is ranging over the C values, and J is ranging over the gamma values. And here we get the cross-validation scores for each fold. And then I average them. So this is like the performance of those hyperparameters. But you can print it out, or I guess plot it as an image. So here on this axis is gamma, and on this axis is C. And then you can sort of visually see which combination of parameters is working the best, and yellow is better. So that you can only do this, you can only visualize 2 or 3 dimensions, I guess mainly 2 dimensions for this kind of heat map thing. But it can be useful because it suggests that something interesting might be happening down here in this region we haven't explored yet. So I made those sets bigger so that I could see more of that picture. And I made it even bigger so we could see more of that picture. And here you get sort of an idea of what the relationship is between gamma and C and the performance of the model. And it looks like there's kind of a ridge here going like along this diagonal here. And so you pick a lot of parameters are equally good. So there's lots of ways to get 96%. 96% cross-validation score. That means that's the average classifier accuracy. across the 5 folds. So that turns out to be the best one. Now you can take those same parameters. So I guess I figured out what they were, and then I did the I fit on the with those hyperparameters. I fit on the training set, and then I looked at the test set, and it does even better on the test set than it did on the training set, and that's typical. Because to get this number, which is 96% accuracy, remember that you're only training on 80% of the test set, and the test set is only 80% of the data. So the model is going to be worse than it could be just because you're not getting to train on very much data to produce this number. So now to produce this number, I got to train on the entire training set. So that's like, you know, a lot more data, 25% more data. And then if you were to test on all the data that you have and then put a model into production, the performance would be even better than this score. So these estimates that you get are pessimistic, and that seems to be like a good idea. You know, you want to consider the worst case. All right, and this process that we've been exploring here, just like checking out a bunch of hyperparameters, that's called grid search. And there's a library that will do grid search for you. So you have to give it some Python dictionaries. So this is just so this classifier that we're going to use is the random forest classifier. This tells you what all of its parameters are. So a lot of these are hyperparameters. We haven't talked about decision trees yet, and hopefully we will. But so like some of these are the number of estimators. So you have a decision tree is like one model, and then there are ways of combining different models. Like these are called ensemble methods. And so the idea is basically like if you can train a diverse set of models that are all wrong in different ways, then you can sort of average their opinion, and then the weird ways, the weird faults of each particular model will cancel out. And you'll by sort of like, it's like two heads are better than one kind of idea. So if you make these models vote, then collectively they might be smarter than any individual model. And that basic idea is ensemble methods, and that's kind of what a random forest is. They call it a forest because it's based on trees. Ha ha ha. So one hyperparameter is the number of estimators. That means the number of trees in the forest. And on each decision tree, there are various ways of doing regularization. So this is like, just think of it as regularization on the individual trees. And these other details, just think of these as hyperparameters. So the way it works is we're going to explore all of these possibilities in this first dictionary. So 3 is going to be matched against 2, 3 is going to be matched against 3, 3 is going to be matched against 4. So they're going to try 9 possibilities for this first one. And then here's another big cross product of possibilities. So now with bootstrap set to false, we're going to try all 6 of these possibilities. So every one of these choices with every one of those choices. So altogether, we're going to try 9 here, and then 6 more there. So that's 15 hyperparameter combinations. And it just does it for you automatically. So you fit the training data, and then it just automatically tells you what the best parameters are. And you can get the best model out, and then you just get the score of the best model, which turns out not to do as well as support vector machine in this case. All right, any questions about that? Okay, so we're going to start talking about neural networks today. And I posted a link on the Piazza to the book. The book has a supplementary chapter on neural networks, which is okay. It also, like, it's not really about deep neural networks, and I'm looking around for a book, but it's not really about deep neural networks. If you want to know about deep neural networks, the hands-on machine learning with scikit-learn and TensorFlow is excellent. So if you do really like neural networks, I suggest you read like the first half of the supplementary chapter from our textbook, Learning from Data, and then look at the second half of hands-on machine learning, where they explain deep learning in detail. So these notes that we're about to go through are pretty much just a direct transcription from the textbook, to the extent that I like feel bad about putting this on the internet, but so this is just going through the textbook. But so what is a neural network? We're going to get deeply into that, but here's sort of an opening attempt by the authors of the textbook, and I think this is really insightful. It says it's a generalization of the perceptron that uses a feature transform which is learned from the data. So it kind of learns its own feature transformation and then uses it in a model. So you can think of each, a neural network comes in layers, and you can think of each layer of a neural network. I guess I'm skipping way ahead here, but I just wanted to get a picture of a generic neural network. So I think most people have probably seen these diagrams before, even if you don't know exactly what they mean. But neural networks come in layers, and it's like each layer can be thought of sort of as a feature transformation of the previous layer. So here's the input layer, and then you get sort of a feature transformation of the first layer, and then the second layer is a feature transformation of this layer, et cetera. And this can go on for many layers, and the sizes of each layer can vary. And this is all like biologically inspired, I guess you could say. Like, I don't know if we talked about this when we talked about the perceptron, but the perceptron is itself kind of inspired by a neuron. So here's a picture of a neuron. So neurons, they collect signals in this area. These are called dendrites, and then there's a long sort of like a insulated cable called the axon, and that ends in these synaptic terminals. And the synaptic terminals connect to the dendrites of other neurons. And so these dendrites here get stimulated by other neurons sending signals across their synaptic terminals. And then if this neuron gets enough stimulation, then there is some kind of electrical explosion that travels along the axon and then activates these synapses. And then that stimulates other neurons, which if they are sufficiently stimulated will then fire in turn. So that's kind of like how just a perceptron works. So the sign function is kind of like the threshold for whether or not the neuron should fire. And this is kind of like, so this is sort of like the axon here. And then these are kind of like the dendrites sending information in. So these are just, this is a perceptron. Everybody knows this is just sine of the dot product of W and X, and this diagram goes along with it. So this 1 is for the bias input. Here's the first variable, the second variable. So instead of writing it as a dot product, you can think of these as being wires with weights. And so the the bigger the weights, the more this input gets amplified. And that also has some kind of connection to biology. So they say neurons that fire together wire together. Neural connections can strengthen or attenuate, depending on whatever learning algorithm the meat in our brains follows. So these weights are adjustable. This is what gets learned by the perceptron learning algorithm. And then this symbol here is supposed to suggest like a step function, like sine, which is 0, and then there's an abrupt transition to being 1. So we're thinking of -1 is like not firing, and then 1 is firing. So that's a transition. We call that an activation function. So it says, it gives the function that determines whether or not the neuron is activated. And everybody knows that the decision surface that you get from a perceptron is a hyperplane because it's just a linear model. Isn't it amazing how many different ways there are just to think of this simple idea? Okay, so now this is transcribing some things from hands-on machine learning about neurons, and I think I just said it all before. So so people were excited about perceptrons back in the 50s. This was an idea proposed by two early AI pioneers called McCullough, Warren, and I think their names were Warren and McCullough. And then later it was pointed out that, hey, a linear decision boundary isn't very exciting because you can't represent all functions using a linear decision boundary. For some reason, this was like a crushing discovery, even though it seems kind of obvious now that, you know, a hyperplane is flat. So in the 1950s, there was a paper by a famous AI researcher named Marvin Minsky that points out that if you have this red region here is like the exclusive OR of two decision boundaries, two linear decision boundaries. And they point out in this paper that there's no way to represent the exclusive OR of two I guess you could call them half spaces, because they're not just hyperplane separations, they're also shaded in one direction. So sometimes we call that a half space. So this red region here is inside the H1 half space, but and it's inside the H2 half space. So this is actually the logical conjunction of H1 and H2, but that's fine. You can't represent that either. So actually the white region would be the exclusive OR. Anyway, so I shaded the wrong region. Sorry about that. I should have just explained it the other way. But okay, so that's a shortcoming of the perceptron model. I mean, now we know you can add, you know, polynomial features, and then you can do a lot more. But I don't know if that wasn't on people's radar at that time. They barely had computers, you know. Okay. Also, this guy Marvin Minsky is he's a legend of AI, but he was also embroiled in the Jeffrey Epstein scandal. He went apparently with Jeffrey Epstein a couple of places, which has not been good for his career, even though he's like very old now. I think he's in his 80s. So anyway, so let's write down this target function, which is the exclusive OR of two half spaces, H1 and H2. So I'm using the notation of Boolean algebra here. So where I write H1 next to H2, that means and. This region would be H1 and H2. But when I put this bar on the top, that means not. So this is H1 and not H2, and plus means or. And then this is saying not H1 and H2. You guys familiar with that Boolean algebra notation? So multiplication is conjunction, that means and then adding is disjunction, that means or. So this is H1 and not H2, or not H1 and H2. So that's XOR. Okay. All right, so we're gonna build exclusive OR using perceptrons. It's gonna take more than one perceptron, and this is gonna be sort of, you know, the first example of a neural network when we get it all together. So first we need a way of saying OR in terms of the language of the perceptron. So you can do that like this. So assume that x1 and x2 are either plus or minus 1, and then consider the sign of x1 plus x2 plus 1.5. Okay, so this is, the sign is going to output either plus 1 or minus 1. So plus 1 is going to be true, and then minus 1 is going to be false. So it adds this 1.5 here. Okay, so so how many different numbers can you get if x1 is either plus or minus 1, and x2 is either plus or minus 1. So if they're both plus 1, then you get 2, right? And then this becomes 3.5, which is true. One could be plus 1 and one could be negative 1, in which case these things are 0. And then you take the sign of 1.5, which is true. And so the only way OR can fail is if they're both false. So that means x1 is negative 1 and x2 is negative 1. So then what do you take the sign of in that case? Then you get negative 2. You get negative 2 and then 1.5. So that makes minus 1/2. So then that would make minus 1 come out. So this expresses OR in terms of a perceptron. You can do AND also. So maybe these diagrams might be better. Okay, and so these are the weights. So this weight is 1. This weight is 1. So if you set up a network like this with these weights, then OR is what comes out. If you set up a network with these weights, then AND is what comes out. So here we did it with 2 variables, but you could do it with as many variables as you want. Do you guys see how you could do AND of like, what if we wanted to take the conjunction of 3 variables instead of 2 variables? What would that be? How would this diagram change? Let's say that I added x3 down here. Okay, and now I want this to be the AND of x1, x2, and x3. So this weight, it looks like it should be 1. Does this number need to change at all?
No.
Okay, so actually, maybe we should think more about the way it works when it's just 2. Okay, so logical AND, that means that x1 should be 1 and x2 should also be 1. So notice that if these values are anything other than both positive 1, then it's going to be overwhelmed by this minus 1.5. So for example, if I have minus 1 plus 1 minus 1.5, this is going to be negative. And so when I put it into the sign function, false is going to come out. So negative 1 will come out. So this 1.5 value actually is specific to just having 2 inputs because with 2 inputs you can go as high as 2, and 2 is the only thing that will overcome the minus 1.5 and make it be positive. So if I were to put in a third one here, then I would have to change the 1.5 to what?
3.
2.5. The reason you don't want 3 is because 3 would overwhelm everything. But you want a little space left over for x1, x2, and x3 to be able to overcome. So now if all 3 of these are 1, then it adds up to 3, which overcomes the negative 2.5 to make a positive value, and then true comes out. But if there's any other configuration here, then it's not enough to be bigger than negative 2.5. And so a negative 1 will come out, which is false.
Is negative 2.5 a bias?
Yeah, that's the bias weight.
Okay.
Yeah, okay, great. And that kind of help, that makes the word bias make sense. So you have kind of a bias towards not firing that you have to overcome with the other inputs. So here's how you can do not. Not is the bias weight is just 0, and you just negate, you just make it negative. So if this is plus 1, it becomes minus 1. If this is minus 1, it becomes plus 1, and then you take the sign, and then the sign of plus 1 is plus 1, and the sign of negative 1 is negative 1. So this implements not. So now we can do logic with perceptrons. So you can put all of this stuff together. So let's try to do the XOR now, this complicated function that broke everybody's heart when it couldn't be handled by a single perceptron. So here's just, this is the notation. We're just fixing notation for describing H1. So that's the first half space. So this is W bar 1 will be the weight vector for that guy. And for this other half space, W2 will be the weight vector. So we'll use this notation for writing these networks. So this is H1. So this is from W1 bar, the 0th coordinate, from W1 bar, the first coordinate, from W1 bar, the second coordinate, and similarly for H2 there. So we've expressed H1 and H2 as perceptrons. And so now we can sort of like start sketching in the rest. So F is supposed to be the exclusive OR. So that is, it's the exclusive OR is just the plain OR. So this plus is just regular OR. So it's, and remember 1.5 is what we put here to do logical OR. So this is this input. So what we have here is just OR. It's just that we're assuming that the input on this wire is H1 and not H2, and the input on this wire is not H1 and H2. So how do you express those? Well, here's how you express H1 and not H2. So H2 has a negative coefficient on its connection, and H1 is just copied, but now you have the minus 1.5, that's for and. So this is H1 and not H2. And so similarly over here, you have not H1 and H2. Okay. So now you can put all of that stuff together. And so this is sort of our first example of a neural network. The book calls this a multi-layer perceptron. And the difference in the minds of our textbook authors is that when you just use sign as the activation function, then it's a multi-layer perceptron. I don't mind just calling it a neural network. So look what's happening here. So these notations are the same as before. So this W1, this little node here is becoming H1, right? So I'm trying to draw that with my mouse, which is a terrible idea. So this becomes H1, right? Because of these red inputs here, just make it H1. And down here, what does this one become? This node represents H2. Okay, and now let's look at these minus. Let's just focus on the inputs here. So this is saying not H1. So this becomes not H1. But because of this, it's anded with H2. So this node becomes not H1 and H2. And for similar reasons, this one down here becomes H1 and not H2. Okay, and now this 1.5 just takes the the OR of these two things. And so the output of the entire network is F. So this is pretty typical of a neural network here. It has a certain number of layers. Just as notation, we're going to call the input layer layer 0, and layer 3 is the output layer. And we call these layers in between hidden layers, I guess, because if you don't know how it works, then these are just a black box. So there's 2 hidden layers. So you would say that this is a three layer neural network. And so every layer has a bias here, a bias that has outputs but no inputs. So notice that the bias node always has outputs, but it never has inputs. And every node in the previous layer connects to every node in the next layer except for the bias. And you can translate what we just did from the diagram. Looks kind of nice and organized, but you can just also write it if you want to as an algebraic expression. So it goes down even further than this. So this is just turning the diagram into an equation. You know, you can do it backwards. So the last thing that gets applied here is the sign of not H1 and H2 and or H1 and not H2. So then you just expand things term by term, and you get this this formula, which is a lot uglier. But notice that it's just a complicated composition of linear functions and one nonlinear function, which is the sine function. So that's going to be true of neural networks in general. So you can always write them out as big formulas, and they're just going to be linear parts and then compositions with some activation function, which is not going to be sine usually. It's going to be something else. Okay. So we did this for XOR, but the same trick works for any Boolean combination of half spaces, and you can still do it in 3 layers. Like here's a more complicated example. So in this example, these plus regions are the regions that we want to contain the positive instances here. And so this, we can express it like this. So not H1 and H2 and not H3. So I think that's probably this one. And then H1 and H2 and H3 is this one. And then H1 and not H2 and not H3 is this one. Okay, so this is using the Boolean algebra notation again, where multiplication means conjunction and plus means disjunction. So how would we organize these things into layers? So the first layer would just take the inputs and then give you the half space functions. And then the second layer would give you the conjunctions of the literals here. And then the third layer would just take the disjunction of those conjunctions. So this is with three half spaces, but it doesn't matter how many there are. It's still going to be 3 layers, but it will have more nodes in each layer. So there could be, you know, hundreds of nodes in layer 2, depending on how many half spaces there are, and there could be hundreds of nodes in the third layer, depending on how. Well, actually, once you pick the number of half spaces, sorry. So once you decide that there are 3 half spaces, then there's one summand here for every Boolean combination of those potentially. So anyway, you can figure out the combinatorics if you want to. All right. So what we've just done basically is we've sketched out a way to express any polygon or any sort of hyperpolygon in terms of a 3-layer neural network. So that's pretty powerful. In fact, that can approximate literally any function, like I mean, not really weird ones like measure 0 weird functions, if you know what I'm talking about, like, you know, +1 for the rationals and -1 for the irrationals and things like that. So there's some pretty bad functions out there. But any smooth function, smooth, nice, normal function, you can approximate it with polynomials. Like here's an approximation of Australia using polynomial. Here's an approximation of a dolphin using a polyhedron. And you can do this in higher dimensions too, with like hyperpolyhedrons. So with a 3-layer neural network, you can represent pretty much any target function that you're likely to encounter. So there must be a downside. And the downside is that you get millions of parameters. And also you're gonna have really high variance with all of those parameters. So you'll be able to fit the training set perfectly, but then your generalization will not be good usually. And then we haven't yet discussed how do you train these things. So it looks like we'll not get to that today, but we will get to it soon. So this is pretty awesome. We've just proved that, you know, any target function can be approximated by a 3-layer neural network. Okay. So now we'll start talking about how do you come up with a a general mathematical description of what we just did. And unfortunately, it's going to involve a lot of letters and subscripts and stuff like that. So please just bear with me here. Okay. So if you remember with the perceptron, we were back in chapter 3 of our textbook. There's this nice discussion about why the sine function is hard to work with. But it's because it's a discrete function, and discrete optimization problems tend to be NP complete. And so in general, the problem of finding like the best hyperplane separation just using the sine function in the hypothesis for the hypothesis class is an NP complete problem. And one way to make this better, which is the same approach that we used last time, is to use a smoother transition than sine. And so the advantage of doing that is then you can use calculus and do gradient descent to find the optimum. So here are some plots. This blue plot here is the sine function, and notice that that's pretty well approximated by hyperbolic tangent. And the approximation can get pretty much as good as you want it to be by putting in little multiples here. So as the size of this multiple increases, you know, this function becomes the sine function in the limit. So you can approximate the sine function as closely as you want using hyperbolic tangent. So we're going to use the hyperbolic tangent activation function, which is a pretty common choice. But there's a little bit of, with deep neural networks, you can still use hyperbolic tangent with deep neural networks, but people in recent years, since 2010, I think, have done some some out of the box thinking that have found ways to improve on sort of. So you might know that there's been this revolution with deep neural networks in the last 10 years, and so the insights that have made that possible are basically two things. One, amazingly, is just it's very important how you initialize the weights when you set up the neural network, and so people have found initialization schemes that work much better. And people have also been experimenting with other activation functions besides activation functions that are sinusoidal, you know, meaning S-shaped here. So this is, you know, kind of an analogy with early attempts to fly. You know, people thought that in order to accomplish artificial flight, you had to closely imitate bird flight, and people were like literally flapping their wings and things like that. So just as artificial flight doesn't require bird wings, maybe artificial neural networks don't require an all or nothing activation function. So here are some other activation functions, which we will not use, but if you want to know more about them, you can read Hands-on Machine Learning with scikit-learn and TensorFlow. So this one is called ReLU, which we've talked about before. So in some sense, the perceptron learning algorithm is stochastic gradient descent with ReLU. So it's kind of too early to talk about what the advantages of these are. When you do gradient descent on a neural network, you do it layer by layer, and so you know, the gradient of this layer will affect your computation of the gradient of the previous layer. And there's a problem called vanishing gradients. So the signal kind of dies out before you get to the first layers in the network. And so these activation functions are designed to make that less likely to occur. So these are variations on ReLU. And there's one that's basically ReLU, except it's completely differentiable. It's called ALU. So you can read about these things online. Maybe we'll play with those a little bit later just to see if they work better than hyperbolic tangent. We have time. So here's a picture of a general neural network. So you can see it's organized into layers. The first layer is just the input layer. This is layer 0. then you have some number of hidden layers, and then you have an output layer. So we'll use capital L, just like the textbook, to specify the number of layers. So each layer has a bias node, and the bias node has outputs but no inputs in every layer, except for the last layer has no bias node. Okay. And where we've written theta here, theta is just the activation function that's being used by the neural network. So we're going to use the same activation function for every node. But there's no reason that you can't use different activation functions for different nodes. It just makes things more complicated. With TensorFlow and these other libraries for manipulating neural networks, you can choose your activation function node by node. Okay, so also notice that this thing only goes in one direction. So these are all sort of, I'm going to regret saying this later, but when you're making a prediction using the network, so what happens? You get some new instance that comes in, so that affects the inputs, and then all of that information goes forward to the next layer, and then these get summed up, and the activation function gets applied, and then that information gets pushed on to the next layer. So this architecture is called feed-forward neural network because the data only flows from left to right. There are no links that circle back around and make a loop or something. People have explored architectures like that. Those are called recurrent neural networks, but they're more complicated. So this basic idea is a feed-forward neural network, and then when the activation function is sigmoidal, then you can call it a feed-forward sigmoidal neural network. So that is what we are studying now. Okay, and what comes out is the hypothesis. So what is a hypothesis class here? Hypothesis class, you're going to fix the architecture, and then once you fix the architecture, a particular hypothesis like this one is just determined by what these weights are. So you can see just from how many red lines there are, neural networks have many weights, and so overfitting tends to be a problem for neural networks because they have so many parameters. But it's the choice of these parameters that specifies a particular hypothesis. Okay.
Sir, so the function, the activation function is only applied to the last layer of the hidden layers, right?
It's applied every time. So there's an activation function. Yeah,
Okay.
there's an activation function here. So what'll happen is here you have a bunch of weighted inputs that are coming into this thing. And then they're going to get summed up, and then the activation function is going to get applied. So it's like the activation of the sum of like wi xi kind of.
Okay.
And then that's what comes out on the other side. And that's what it spits out in both of these lines will be that.
So it's applied to each nodes.
Yeah, that's right. The activation function it lives on each node. Oh, and if you're doing regression, so if you're doing classification, then what will come out is like, one big sigmoid, and then you can use that. You can threshold that and do classification like we did with logistic regression, or you can just leave off the threshold on the last node, and in that case, you just get a big weighted sum of these inputs. I'm using xi here, but it's really just this thing, whatever. So if you take off the last activation function, then the neural network becomes a regressor. So you can use it for regression. If you leave the activation function on, then the output is sigmoidal and it's better for classification. So you can take off the threshold on the end and make it better for regression. And some people just leave it off, and then there's that trick where you can do classification using regression by just applying the sign function. So you could do that too. So we'll look at all those possibilities. Right. So now if we were to write all that down as a formula, we could, and it would just be a composition of this theta, whatever that is, which is going for us is going to be hyperbolic tangent and linear functions. And so somehow in order to do gradient descent, we need to implement the gradient of this monster. And so that we're going to write down all the notation and for doing that, and then the neural network assignment, you actually will do it. So it's definitely the hardest thing that we've implemented. So one thing I think that is surprising maybe about this class is like here we've gone through and we've implemented like 4 or 5 of these powerful machine learning techniques, and most of them, if you use the NumPy library, it's like not more than like 5 lines of code usually. Just like they're amazingly simple, but the neural network is a little bit harder. Okay. So we need to manipulate the gradient to do gradient descent, and if you just try to like straight up compute the gradient, then it turns out you end up doing a lot of redundant work. You know, like if you do this using the chain rule, then when you take the derivative of this one, then by the chain rule you need to compute the derivative of all of these. But also when you take the derivative of this part, then you also need to do the derivative of all of these previous ones. And so you end up duplicating a lot of effort. So there's this really smart way to do it called back propagation that was invented in the late 80s. And it's a dynamic programming method, if you have learned about that in your algorithms course. So that means sort of like a lot of steps get combined, and a lot of the unnecessarily repeated work gets eliminated. So this was like this sort of brought neural networks back to life for a while in the 90s, and then they were too slow to train, and they also, it was hard to make them deep in the 90s, and so then they sort of went to sleep again. So they call these things summers and winters, you know. So there was a summer when Perceptron was invented, and then there was a winter after Minsky pointed out that you couldn't express exclusive OR. And then there was a summer when back propagation came along, and then there was a winter when they sort of reached the limits of those techniques. But now we have deep learning techniques, and we also have GPUs. So GPUs can train these things quickly, and so that sort of solved the problem of it taking forever to train them. Okay. All right, so now we're just gonna fix the notation. Like you might wanna copy all this stuff down yourself and kind of practice with it a little bit if you really wanna understand the algorithms. So little l is gonna be the layers, and so it'll go from the 0th layer, which is the input, out to L, which is the output layer. And DL is the dimension of layer L. So just to give an example, let's figure out D2 in the neural network that we've already made here. So let's come back up here. Gosh, okay, so here is, here's layer 2. Whoops. So D2 will be the number of nodes in that layer. So it'll be 1, 2, okay? It's not 3, it's 2. You could think of it as going 0, 1, 2. So in this network, D2 would be 2. Okay, so coming back. Nodes in layer L are numbered 0, 1, 2, ... DL. And so 0 is the bias node. So the architecture is just how many nodes are in each layer. And so if you want to use the same activation function for every node, then once you specify the activation function and the number of nodes in each layer, then you've completely determined the architecture. So that's sort of the graph of the neural network. So, you know, here we've decided that the input layer is length D, and this one is length whatever. So once you decide how many nodes are in each layer and how many layers there are and what the activation function is, you've determined everything except for the particular values of the weights. And so we call this information with excluding the weights, the architecture. And that gives you the hypothesis class. So the hypothesis class for a given neural network is specified by a vector like this. When you use the multi-layer perceptron object in sklearn, you literally give it an array like this to specify the architecture, and then you also tell it the activation function. So a particular hypothesis is just something you have to choose values for all the weights. So that's something that's determined by training. And yeah, so there's one weight for each node in layer L-1 connecting to each node in layer L. So the notation for the weight, this is triple indexing. Okay, so this is the weight of the connection from node I in layer L-1 to node J in layer L. That's what WLIJ is. So here's a little bit of a picture. So this is the output. Xi is the output. We use this superscript in parentheses. It's in parentheses so it's not confused with exponentiation. But this is the output of node I in layer L-1. And SJL is the input of node J in layer L. And then its output is XJL. Okay. So this diagram I copied from the book, but it's a little bit misleading. So this SJ, so what this is node J and layer L. So all of these inputs come in and they get summed up. So here's an expression. So they get summed up, and then they get exposed after they're summed up here into a single number. They get exposed to the activation function. So that's what this is saying here. So the output is just the activation function theta applied to this sum. And then that becomes the output for node J and layer L. And then that gets copied out on all of the wires that emanate from this node. Okay. All right. You can express this as a vector. It turns out that these, even though there are like lots of connections here and it looks like a big mess, we're just going to think of all of this stuff as being matrix multiplication on this vector, which is the input, and then the output will be that vector. So once we get done with all this stuff, it will actually be fairly simple. It'll just be this vector times a matrix is equal to this vector. So that's what we're working out right now. Okay, so S is the vector of all inputs in layer L, and this is the vector of all outputs in layer L-1. So notice that for the outputs you have a bias. So this is just 1. So the output of the bias node is always 1, and so you also have this extra dimension. So this is the number of nodes, DL-1 is the number of non-bias nodes in layer L-1, and then there's an extra dimension for the bias. But for the inputs, the bias node doesn't have an input, and so this is just the same as the number of non-bias nodes in layer L. Okay, so you can, this gives you a big clue that there's going to be some matrix product coming. And so this J here is fixed, and this J is fixed. So this is like the dot product of the sort of X bar with some vector here, which is these W's with I varying and J fixed. So that's going to be kind of like a row of the transition matrix. So WL is the transition matrix that goes from layer L minus 1 to layer L. And so its entry is IJL. So this is all incredibly dry, I'm sorry. So then the ith row of WL is the weights leaving node I of layer L minus 1. And the jth row is the weights entering node J of layer L. So just with this notation, it has these dimensions. So this is the number of so this is 1 for the bias node plus the number of non-biased nodes in layer L minus 1. Those are the inputs, and then the outputs are there are DL of those. When you actually compute S from X, you have to take the transpose because we want it to, the dimensions have to work the other way. But anyway, so here's the equation for the inputs to layer L as a matrix product of the outputs from layer L minus 1. Once you get used to it, it's not so bad. And then the set of all weights in the network is just, we're going to use W bar to describe it. And it is the just the vector of all of the weight transition matrices. I mean, the layer transition matrices. So then here is the total number of weights, which can be pretty big. So what this is doing is it's just this is the number of weights in WL, and so we're just adding that up for every L. And if you have a network with this architecture, so five variables including the bias, and then one layer of size 5, and then an output layer with just one node, then you get 66 parameters. So maybe more than you would expect, because there's lots of connections going on. So this is a good place to stop. And so probably you guys are just like, I actually have no idea. What are you guys doing? Are you okay? I'm going to stop sharing this and stop recording.